Hello. My name is Sergiy Migdalskiy, and I work at Valve with Dirk Gregorius. I help port, develop, and optimize our in-house physics engine, Rubicon. I also have implemented physics engine for Uncharted Drake's Fortune, a PlayStation 3 title, many years ago. Can I have a show of hands? How many of you are working with the physics engine on a daily basis? Okay, that's a fair amount. How many of you is working with any complex C++ software on a daily basis? That's pretty much everyone. So you guys are in the right place. Because while this talk is about physics development and debugging of physics engine, I'd like to emphasize that the tools and techniques I'm describing are general purpose. They are probably applicable to any complex C++ software. I'd like to show you what I do the whole day long. This video is accelerated about 10 times because I don't want to show 10 minutes of me playing with the ragdolls, but this is the representative sample of what I do. I'm trying to play with the ragdoll to see if any constraints are breaking. So constraints don't break. So I'm just piling up a bunch of ragdolls. This is like accelerated like 30 times. And I noticed something weird. One of those ragdolls doesn't work right. It doesn't collide with anything. What's that? I'm panicking. I'm trying to see if some ragdolls are, yeah, they're all working but one. But why? I'm clicking on this ragdoll and I'm noticing something. The collision flags on that ragdoll, on this one, the one that doesn't collide, they are different. Basically, it turns out that the first ragdoll I spawned here is spawned saying, I don't want to collide with anyone. So the mystery solved. I go on to other very important tasks. Yeah. We started working with Dirk by porting his rigid body engine to Valve's framework. I knew Qt, and I like playing with stuff I'm working on for fun and to make it easier to show people our progress. I implemented a little IDE for our project. The development was incremental. The result that you see is a result of me adding a lot of stuff over like a year. Every time it took more than 30 seconds for me to look something up in debugger, I decided that I will spend 15 minutes and make a physics widget to look up a position, velocity, or the list of contacts. And it took me 15 minutes to implement that for the first time, but it saved me time ever since. And the effect is accumulative. I'm making a lot of these widgets, and every single one of them keeps giving back time. So in the end, it was much more pleasant to develop than at the beginning. So we had the physics running in an isolated tool with buttons, sliders, 3D window with shadows. Shadows are pretty good for debugging contacts because you can see whether objects are hovering on top of each other or touching each other. It restarted in a couple of seconds, which is great for iteration time, right? So it was a rapid development time for us. It didn't last very long because every game physics engine has to be integrated into a game. Once we integrated our game physics engine into the game, we had to debug it within the game. We lost our fast iteration nice UI. Every game engine has in-game visualization. For example, to debug draw the physics collision. We make do with it. It has some serious drawbacks, though. You can't easily use the mouse cursor to click these things, like you do in the UI. You can't fly around easily, at least not until you implement a special camera for it and integrate it into the game. And you have to switch to this camera with something, some button or something. It's just not convenient. You need to render inside the game engine. And depending on the render you use, you probably have to implement a special shader. And you have to maintain it. Every time render engine changes, you have to change it. You have to implement a special pause because you want to examine instantaneous state of physics. And that can be non-trivial, especially in multiplayer and game server environments. And finally, it's not very trivial to implement the UI. You've seen the things that I could click in the previous video. That kind of UI is just very hard to implement in most game engines. So Physics Testbed, that's what we called our tool, was a great UI with a bunch of physics-centric widgets that we already developed. It was great help already in making physics work. I felt I can reuse it in the game integrated physics. But how do we display in-game physics in a separate window with widgets and mouse and everything nice? I briefly entertained an idea to open an extra Qt window in the game process. It's not that hard because I already have the QMain window, all the code that opens the window. After a day of experimenting, I found it very inconvenient. It's intrusive to the main game loop. You have to take care not to intertangle the message pumps from the game code and the Qt. You either have to run Qt in a separate thread, which creates a host of problems when it interacts with the game, or you have to integrate it in the main game loop, which is basically you don't want Qt in your runtime. You still have to implement full pause in the game. This thing still doesn't work if the game crashes or if it's stopped in a debugger. Anyway, ultimately I decided against it, but this is probably the simplest to implement solution. Deciding against it, I decided to visualize it in external process in my tool that was already external utility. But to visualize an external process, you need to send data to the external process. The hardest part about sending data to the external process is converting the data into a bit stream. Once you do that, it becomes pretty trivial to send it over the wire or in many other ways to the other app that visualizes it. One of the nice features of having this out of process, though, is that you can play with it. So, serialization, the biggest obstacle here. But once we solve it, it becomes very useful. We can save and look at something later. We can implement nice data profilers and time CPU profilers. We can record and replay bugs. It's a good thing to have. So it's not a hard thing to decide to implement serialization in your physics engine. And by the way, of course, serialization means that it works in two ways. The external app has to somehow convert those bits into the data structures. So how do we serialize? Physics engine is complex. There are so many classes and data members and pointers. Pointers are hard to serialize. And we need our software that doesn't miss anything, that reconstructs everything faithfully, hopefully updates itself every time we add a data member, or delete it, or change its type, or change its name. Well, I can tell you what I don't want to do in this case. I don't want to write the code by hand. We can analyze the engine's header files. The header files in the engine contain full description of all the data in the engine and how it works. That's what we would do if we did write the serialization by hand. We would just read the header files, understand the data structures, and wrote the code. But instead of doing it by hand, we can parse C++ in a utility and spit out the C++ that will serialize stuff. But parsing C++ is extremely hard. It's notoriously hard. Or is it? Not with Clang. What's Clang? I hope a fair amount of you know what's Clang. Can I have a show of hands? That's great. That's great. It's an open source C++ compiler, to those who haven't heard of it. In some ways, it's a direct GCC competitor. But it has much more readable source code and liberal license, at least in my personal opinion. Clang makes C++ parsing a piece of cake. It's written in C++ itself, it just works. We can use all our existing code as input, convert C++ and header files into easy-to-use AST, and spit out serializer routines. One bonus from Clang that we had is we improved our C++ compliance and we prepared our code base for Linux compilation. It's a very nice thing to compile a code base in more than one compiler. I mentioned this term, AST. It means abstract syntax tree. It's a tree that describes everything there is to know about your source code. Maybe minus the white space, but even white space, it does describe everything in a convenient tree data structure. This is how it works schematically. For every class, you'll have a node. For every member of this class, you'll have a node. For every type or the size or annotation or anything you can think of in your source code, you'll get a node of some type. So you get all the information. In effect, we're transforming C++ code into additional C++ code using Clang that parses the source C++ code. So it's very tempting at first to print the output using a bunch of printf statements inside your parser. And that's a bad idea. I decided to resist the urge, and I consider myself lucky. It would be horrible slow and unreadable if I just printf'd my C++ code. So parse, then generate, decouple these two things. And unless your project is trivial, you'll be rewarded. I'm distilling the huge AST of the physics engine into a very concise JSON file. JSON is a human-readable data format that's used very widely on the web right now and very known. After adding features for a year, my visitor class that uses Clang libraries is about 1,000 lines long. And again, it would be incomprehensible if I generated code right in the parser. So printing the JSON is a nice alternative. Again, here's how the JSON works, just so that we are clear on that. There is the source code of my physics. There is this class, capsule shape. I'm just generating the key in the JSON, capsule shape. And I'm interested for the serializer, I'm interested in the fields and the data members. So for each data member, radius, I get a type. I actually need the type for it. Center, also type. And by the way, it's an array. So I'm adding a key saying array size. By checking the key, I can check whether the NV center is an array or a trivial data member. Also, I need to serialize the base class first. So I need to know which base classes there are in this class. So I have another key with that. So I'm taking my C++ code, let Clang parse it, and spit out JSON. But ultimately, I need my serializer and potentially other useful tools, a little bit about it later, to be written in C++. This raises this question: how do I generate my C++ code from JSON? Fortunately, there is no need to reinvent the wheel, because the wheel was invented many times before us. There are a lot of text template libraries and even languages written specifically with this purpose in mind. They are widely used and freely available. The one I chose is called String Template. It's a text library that's very readable, very easy to use, very declarative, and very well suited for code generation. You could use something else. In fact, if you are very familiar and comfortable with, say, PHP, you should absolutely use it. You could also use XML. In fact, the standard Clang tools can output full abstract syntax tree in the XML format. It's a little bit slower than just outputting what you need, but it does a great job. And if XML is your thing, and you know XSLT, which is a great, powerful transformational language for XML, then this might be your pipeline. String template and JSON are just very easy to learn and very easy to debug and are very much human readable and very easy to show to other people. So that's why I chose them. But there are many ways to configure this pipeline, and I'm just describing what worked for me. My string template looks like this. The tool itself, by the way, is written in Java. but you don't need to know Java to use it. It's just a command line tool. All my serialization, unserialization, and memory statistics code is generated from 400-line template, or 410-line template, or so, something like that, and it doesn't change ever, almost never. These are a few of these lines. They auto-generate the code to serialize most classes in our physics engine. You feed the JSON, it spits out C++. It's quite simple. So to recap, we start with the source code of the engine. It's arbitrary C++, potentially annotated. For instance, you can annotate only the classes you want serialized. You can exclude some field from those classes. And you can add a member call after serialization. More about it later. The parser and Clang part is probably the most interesting part of this, and it's moderately complicated. I wrote the first working version in about a couple of weeks working part-time. Then I fiddled with it for well over a year by doing very minor changes every month or two. It handles all the special and edge cases in our engine, but it doesn't parse any known data structure known to man. If it did, I would have to spit out the full AST, and in that case, I might as well just spit out the full, dump the XML using the standard Clang tools. Anyway, this code is very stable. I made the last change to it about 4 months ago, and the change was very minor. This particular slide shows a useful method that looks for a method with a given name in the class. The record means a class or structure, or struct. So I hope it's clear to see that it just iterates in an STL manner from begin to end, all the methods in the class, and checks for the name. If the name is the same as I'm searching, I'm just returning the method. The best source of information for me was the online Clang docs, especially the class diagram. It's very logical, very educational, shows a lot about how C++ is structured. Also, Clang itself is very, very readable. If you had some experience with GCC or debugging into GCC, it's completely different. So I very much encourage you to debug into Clang and just spend 10 minutes, and it will be quite clear what each method is doing. The generated JSON file looks like this, and I already explained what it entails. And the string template also providing for completeness. But here there is a string template with the generated C++ code from that string template. The template goes through all data members of the class and generates code for each of them. It's smart enough to know where I have arrays, templates, pointers, and so on. All the non-plain data elements are recursively serialized by other overloaded serialization functions. Sometimes I use the methods to serialize, sometimes the free functions. Free functions are very convenient for serializing some third-party structures from third-party libraries, because I don't want to touch the headers from those libraries. Anyway, once you complete these 5 easy steps, you'll have yourself one wholesome serializer. It will be self-maintaining. You will forever be able to visualize all your physics data in all its details. Sometimes we don't even know something is wrong. Some bugs ship and go unnoticed for years until they bite us. This will never happen to you again, ever. Well, maybe I can't make such guarantees, but I really hope that I convinced you that visualizing stuff is good, and that having serializer auto-magically generate itself is even better. We have some more stuff to discuss before we wrap up, though. Here's an example of the workflow that you can have once you have full serialization implemented. So I noticed something weird with an object in this level. There is this lamp that's falling down. So this is the state of the snapshot of the physics engine that I snapshot from the test bed. So I'm looking at the lamp, I'm enabling interaction and start simulation. This is completely independent of the game. And it becomes very clear why the lamp doesn't stand on its base, because it's top heavy. The center of mass is basically too high. When I figure out why it's not standing right, and I can copy the state of the game again and make sure that that's the case, and play around with it some more, I can save it to a file. And the saved file, I can open it later to examine this scene, or I can send it by email. Oops. So I'm turning off my shadows. I can save, load, and it's completely functional physics scene. So this is the kind of interaction that you can have once you implement it. Here's the Clang's Hello World program relevant to this use case. It's called Clang Check. It's a great starting point for any parser that you write with Clang, and it's part of the Clang distro. I urge you to have a look at it if you want to parse with Clang. It uses a visitor pattern. For every top-level declaration in your source that you are parsing, such as a function definition, a class, or a type def, or a global, you get a callback. In that callback, you can drill down the AST. This example is self-contained. You probably can see the handle top-level decl callback that you get, and it has the dump XML method call. This is the full parser using Clang that dumps in XML the full AST of the whole file. So if XML is your thing, this might just be your parser in its entirety. What do you need to parse then? Typically, all our class declarations and data type declarations are contained in a header file, or in multiple header files. So it's enough to just make a CPP file that includes all those header files. And you just parse that one CPP file. It takes a second. And you have the full information about your physics engine. There's absolutely no need to parse the whole engine, except you're doing something that requires analysis of the code, or if your data structures are scattered all across all the CPP files. To parse that file, you need to create a compilation database. Here is an example of one. The most interesting options are highlighted here, and I took out the non-interesting options, like the include path and such. Compilation database is like a makefile, or VCProj. If you don't want to do anything very non-standard, you can simply generate a JSON file. This compilation database is in JSON format, and feed this to Clang. We use a tool to generate our VCProj files in our daily development. We just change the tool to spit out this compilation databases, and it works fine. So here is a little cheat sheet. In your parser tool that you carefully link with all the pertinent Clang libraries, what do you do first to start a parser? Start with implementing an AST consumer on the left. Then implement a factory that just returns an instance of said consumer. Then in main, open compilation database and run an instance of Clang tool. One thing to remember, you have to flush std_err and std_out. Basically, this is it. This contains the whole parser. Before going further and giving you more examples, I'd like to clarify what I mean by the term boxcast. because it's used very widely in our engine, and like raycast, it's like a raycast, but with a box. You move a box linearly until you hit something. At that point, if something, you sometimes want to create a point, and sometimes you just want to use it for further casts. But our engine does it a lot, and AI uses it a lot, so this is a very common thing to debug. Let's see what we've got for our efforts so far. Here is a game running alongside visualization tool. I'm walking around a room, and I'm looking at the raycasts and boxcasts our AI is making. And our player movement, too, uses a lot of these boxcasts. I can look at it from the third-person view, if necessary, if I can't see anything through those walls. And sometimes it can be pretty entertaining to see what the AI is doing. So in this particular example, I found something strange. There are too many boxcasts in some point. Like right now, you see it's flashing, it's scattering. Just a flurry of boxcasts. So I found a place where it happens, and I'm looking around. It looks like rotating doesn't change anything. So why? What causes this? I'm looking around this area, and I'm noticing something. It's the lamp. Well, what if just looking at the problem does not present an obvious fix? What if we actually have to debug code? That's a dreadful thought. When you debug your own code, you easily see the parts, the components, what they are supposed to do, where they are moving, how to check, and whether they are doing what they are supposed to do. Working with a team, it's different. There are lots of moving parts. It's hard to see the whole picture. And it's hard to check whether the parts are actually moving in the right direction and then they are doing what they are supposed to do. And when I find something in somebody else's code, usually there are many ways to fix it. I'm never quite sure which one is the best. Maybe I misunderstood the code and I will fix something by breaking something else. So it's important to make it easy. And what do we have? The basic debugging tools are very, very simple. We have the watch window and printf. It's inadequate comparing to the task at hand, which is pretty hard. And now we have this wonderful application. I wonder if we could use it when we step through the breakpoints, just like we use it when we walk through the game. We need to leverage it. But how? The usual debug experience consists of sifting through watch windows, stepping through lines of code, and imagining our 3D world in our mind's eye. Well, I prefer to see the 3D world on the monitor. Ideally, I just want to see it like physics testbed renders it. I also want it changing just in time as I step through my breakpoints. I want to be able to fly around the physics world frozen on a breakpoint, and step and then fly around some more. That would make it much more comfortable, and I would be more productive. Let me show you what I mean. As you can see, this is the place with too many box casts. So the question is, who casts those boxes? I can place a breakpoint in the box trace function. And every time the breakpoint is hitting, I can look at the 3D world and I can look at the last recorded raycast, or boxcast in this case. If I do that sufficiently long time, probably about 60 seconds, then I find the offending box cast. I can look up the frame, the stack frame, and I can again step a few times to see if this is the box cast that I'm hunting for, and looks like it is. And looks like there is like a for loop in our AI code that just seems to cast a bunch of boxes for some reason. I'm actually looking at the name of the function that does it, and it says find free space, and it looks like it just can't find the free space because of that len. The test bed in this case effectively works like a watch window, and that is what I meant. That is what I meant by this. The method that lets us do it is called ReadProcessMemory API. The physics testbed, acting in a way like a debugger, like you just saw, reads memory from the game without the game even knowing it. That's why it's possible to do while the game is stopped in debugger. I call this technique snooping. There is no way for the debugger to alter the game state, which is very nice. It's safe. It works when the process is crashed as well, not only stopped in debugger. There is no activity required from the game. That's the key part, because the game cannot do anything while you are debugging it. The game needs to advertise the pointer from which I need to start looking through my data structures, but that's very simple to implement. It will probably need a mutex so that I can do the same thing while the game is running without stopping it in debugger, just for convenience. That's another thing, also very simple to implement. The interesting thing there, when I thought about this idea, was how fast it would be. Would it be fast enough or not? So I wrote a little benchmark. It is not very fast to read every 4 or 8 byte data field in your engine. Because every time you call read process memory, it descends into kernel, it does a syscall, it costs you 1 microsecond at least, probably more often. So that limits your bandwidth, or effective bandwidth. Reading 4 or 8 bytes should cost you 1,000 times less. So instead of doing that directly, I simply implemented a software cache layer in the physics debugger, not to be confused with the Visual Studio debugger, by the way, that reads 4 kilobyte pages from the game side. You can always read the 4 kilobyte page if you read 1 byte from it. That's one of the basic premises of the architecture on PC nowadays. So there is no potential memory fault when you do that. The cache helps a lot with reading things like C null-terminated strings, because, for example, to know how much you need to read 1 byte at a time until you meet the 0. It would be very slow if you just read 1 byte at a time by snooping every byte out of the game. And it helps generally simplifying the process. So we can snoop the bytes from the game physics, but how do we know what to do with them? It's just data, just raw data. In fact, working the memory of the other process is very much like serialization. If you know your data structures, you can traverse them in another process just like you do that while you're doing serialization. You're just traversing your data structures and writing them out. It's the same thing. We can use Clang to understand our data structures. We can use all our existing code as input and spit out, along with serializer, the Snooper. Just like with serializer, we are transforming C++ code into additional C++ code for Snooper. Something is becoming clearer now, or at least I would hope so. Generating code as a bunch of printf statements in the parser would be really awkward, because now we have to generate serializer, unserializer, some statistics, and the Snooper. and probably some more tools if we invent them later. So we still generate the same JSON file that we use for serialization. Here is a string template for the Snooper. It's different. That's the main different part here. It's pretty small and stable. All my Snoop code for the thing that you've seen, it generated from the 200-line template. These are a few of those lines. They auto-generate the code to Snoop most classes in our engine. You feed it the same JSON file as the serializer, and it spits out the Snooper C++ routines. It's that simple. This is the template and the resulting C++ code. I'm snooping the whole struct into the local copy and then copy out plain data elements. All the non-plain data elements are recursively snooped just like with the serializer case. And the template is pretty smart enough to know where I have arrays and pointers, templates, and so on. Here is the correspondence. So the text goes to text, so I just generate a snoop function for every single class in the engine. For every single class that has a base, if it has a base, I need to snoop the fields from the base first, so I call that. Now, for each field, each data member, I'm snooping it. You see that the radius is snooped like by just copying it from the local copy. And the vector, I'm presenting the vectors as general classes, so they are snooped with a separate function. I didn't include the code for the template that's called snoop field on the left because it would take more space. In the end, I like to call final function to create vertex buffers and index buffer for debug rendering if it exists, if the function exists in the class. And that's what I'm doing. If the post-init method exists, then call it. Here's the full pipeline at a high level. We take C++ file, just one file that includes all our physics engine data structures. We feed it to Clang-derived parser, which is a class derived from AST consumer, that spits out JSON. JSON with all the classes, with all the fields for each class and all the information. Then we feed the JSON to the string template, which generates the C++ code, which we can now compile for snooping and serialization. Let's see a little demo of what we have as a result of all our efforts. Aaron said in the first talk today that we use iterative solvers. Absolutely. I think that it's very important to understand the convergence of the iterative solver. And Aaron was talking about it. So here I want to understand the convergence of this line of hinge joints. All the hinge joint axes are vertical, and all the bodies are initially horizontal. So in the ideal world, it would be just like a chain that moves like this in the horizontal plane, but it sags. It sags because we have just like 2 or 3 iterations there. So I want to see what happens in the solver, in the innards of the solver. How does it happen that it sags exactly this way? Now, I stopped it in the debugger, so I can't click in that application anymore. So instead of that, I'm starting another application, another test bed, and one test bed will be debugging the other one. So I'm running the engine in one, and I am using the other one as a watch window. And you see, every time I press F10 a couple of times to run a projection on one of the joints, I can see how that joint got resolved and broke the other joints around it. So again, one test bed debugs the other. One testbed works as a testbed for the physics engine, and the other works like a watch window. So one physics step was debugged. Now I'm clicking to start another physics step. It hits the breakpoint, and I'm switching to my trusty watch window. This is the state now. And it's especially visible. The first joint, you see it was horizontal, and now it will be like 45 degrees. This is why it doesn't work. Or rather, this is how it works. The iterative solvers is a poor man's way to propagate the energy in the system. This is what we achieve if we implement the serializer and Snooper. This is the workflows. Many more are possible, obviously. Fixing stuff, whether it's yours or not, is unavoidable. At least if you make anything complex. But the faster you can drill down to details, the more efficient you are. The more time you spend developing something rather than fixing it. Once you make debugging 10 times faster, it becomes feasible to do something that was infeasible before because of the debugging cost. This will not work if you send a rover to Mars, because it needs 100% reliability. But we are making games, so 99.9 is fine with me. So higher productivity is worth it. Our testbed tool is for divide and conquer style of debugging. It makes debugging physics world quick and painless. That's why I asked at the beginning who has been working with complex C++ systems. Even though these techniques are presented as physics debugging techniques, in fact, they are general enough to be used with any complex system. And they are presented in this context because I was using it in this context. For example, we have a collision filtering system, and time to time something is not colliding right in the game. You've seen an example of that at the very beginning, although that was not in the game, but in the game we have that all the time. So what we do, we just fly around, click the object that doesn't collide with the other object, and drill down to their flags. In more than 50% of the cases, that solves the problem. Even an artist can do that. That sounded a little wrong. Even a non-technical person can do it. And that's very important. Like this improves the iteration time. So that's the power of visualization. Another example. We had an incredibly slow physics. It worked fine, but it was very slow. All contacts looked very well and correct. When we snooped and looked around, and it looked very well. But when we click around, we've seen that the lists of contacts are too long. We generated the same contact on top of itself many times. And it was possible to see that only when we saw that from another perspective, from the perspective of the UI that we have. We have very rich UI there, written with Qt. That's the power of visualizing something in a way that's not exactly in-game visualization, that's out of game. So one of the technical things that I mentioned briefly before is basically thread safety. You cannot use Visual Studio Watch window while the game is running, for obvious reasons. But you can click the snoop button and it will work whether the game is running or not. So while the game is running and you're snooping, it does take a couple of milliseconds to snoop. While you're doing that, your data structures are changing under you. So that's basically useless to try to do that because you will crash. You will not crash the game, but you will crash the snooper. The way around it is pretty simple. You just create a mutex, and you lock it when you start your physics steps, and you unlock it when you stop your physics step. If your physics step is very long, like your physics is one frame latent, and you run your physics in parallel with the rest of the game, you just create the mutex, you lock it at the beginning of the frame, and you unlock it at the end. let it be like a small window of opportunity in the end. Windows will take care of scheduling, and it will let the snooper have its time slice and will snoop. So that's fine. You can think of it as having the mutex locked all the time and unlocking it for a brief amount of time once per frame. That works too. Another consideration, sometimes you would put a breakpoint in the middle of some internal loop in the engine and the data structures are not in a good state. For example, you put a breakpoint inside the loop that rewires your double-linked list of contacts. In this case, the snooper will crash. So just to provide a better user experience, I just put try except block around it. That will catch any crashes. It's technically not safe. I wouldn't do that if I ship this tool commercially, but it works to improve the user experience. And de facto, what does Snooper do? It just reads some data and allocates some data. If it drops those pointers on the floor a couple of times, it doesn't really matter in the tool. We're talking, again, about the testbed, the watch window, the discardable piece of data, not in-game data. Just to be clear, structured exception handling, that's the try except block, is a Windows-specific mechanism. It's not the same as the exceptions in C++. While with many compilers, if you do try and catch ellipses, it will catch a crash. It's not guaranteed in all compilers, and you need to enable C++ exception handling, which we don't in our game. And try except will catch any kind of Windows exception without enabling this in your compiler. When the game is stopped on a breakpoint, you can just ignore the mutex. You can time it out too. The data structures don't change when the game is frozen, so there is a high chance the snoop will succeed. In fact, for me, like almost always it does succeed wherever I stop, because usually I stop on a breakpoint on a source code line, and usually the data structures are intact there. Sometimes we need some annotations in our source code, and that's what I mentioned before in the slide about adding annotations to exclude some data, include some classes, and exclude some fields from serialization, and maybe call a method or two in the end of serialization or snooping. This slide is a little cheat sheet about how to extend C++ semantics with Clang annotations. The attribute is the keyword here, and in the slide on the left, you see node to control pointer, and I'm basically adding the semantics that says, okay, this is a pointer to uint16, and the number of uint16s it's pointing to is in mn node count. This is something that C++ just doesn't have semantics for, and they just added it. And these literally two macros, this is all that's needed to add this. And on the right, you can see the code that you put in your parser to recover those annotations. So it's pretty simple. I'd like to talk about a couple of less trivial cases, like classes with vtables. How do you snoop a pointer that you don't know ahead of time which class it is? I auto-generate a function for each such class, for each base class and for each leaf class, that creates an instance of each class with vtable and copies its vtable pointer into a known place. The known place is basically an array inside my physics world structure, and I'm publishing the pointer to the physics world, so the snooper can just easily look it up. The snooper can then read the array and use it to recognize the class type pointed to by the pointer. It basically is a RTTI that works across process boundaries and is based on the vtable pointer. This is how I generate the code with string templates. I just go through all the classes and register class. Register class just adds the class by name to the table. And I'm actually printing the comments for classes that I don't need this thing for. And this is the generated code. This is how it looks like. It just initializes. You don't have to add an entry to this when you add a class. You don't have to remove it when you remove a class. Or you don't need to update it when you add a virtual or remove all virtuals from your class. It's all automatic. For some data structures, it's just easier to write serialization code by hand, though. The code generation should know about leafy data types like int and float, and generate serialization code automatically. There is no problem with data structures only consisting of those simple data types. Those can be simply copied directly from another process address space or from the file, from the bit stream, whatever. It's a bit more involved with pointers. In general, C++ doesn't provide enough semantics, but you can add the semantics like I showed in one of the slides before. For example, for the count of the objects that pointed to by pointers. We don't use multiple heaps in our physics engine, but if you do, you'll have to provide some kind of semantics to let the Snooper or serializer know what kind of heap you want your objects to be allocated from. But in some strange cases, like you have an integer that works like a pointer, but with the lower 2 bits having some special meaning, or a unit that has, or a union that you have to run some code to determine how to interpret it. The easiest thing is to just write a little routine that serializes and snoops this by hand instead of automatic. This is just a judgment call. You can make your code generation really, really smart, but then it will be hard to maintain. You can make it really, really simple so that it doesn't understand anything, and then you just implement everything yourself by hand. Some statistics that I thought might be of some interest. We currently have 46 non-trivial classes with 320 fields for which serializer and Snooper code is generated. And by the way, I generated these statistics by looking at the JSON file, also something interesting to note. The parser that Clang, that uses Clang is about 1,000 lines long. It has a lot of, basically it has everything I've ever wanted to print about our AST. I probably spent a couple of weeks part-time writing it initially, and then I've been tweaking it a little bit every couple of months or so. The JSON that I showed snippets of before is about 2,800 lines. The string template, the Snooper is generated from 200 lines, and the serializer, unserializer, and also the memory profiler that walks all the data structures and counts all the bytes allocated is about 400 lines. They unfold into 2,500 lines for the Snooper and 5,600 lines for serializer. And the big win for me personally here, the Snooper and serializer code is massive comparing to the templates. And it changes a lot. The templates barely ever change. And I really don't like writing the serializer or Snooper, well, serializer is more common, code by hand, and changing it every time I change my data structures and keeping it in sync. That's just horrible. Instead, I just have a utility to run every time I change something. And it updates everything. And it never makes a human error, which is great. It takes maybe 2 to 8 milliseconds usually to snoop a typical game frame. Normally, it's in the 10 megabyte range. A couple of more thoughts, because we have time, it seems. Every game physics engine eventually gets integrated into a game, like I mentioned before. It makes change, compile, test iteration much longer. Especially when artists start building these huge, enormous levels, and new exciting physics bugs crop up, that only show up in this map once in a blue moon. makes bug hunting mind-numbingly slow, because the game code is much, much larger than the physics code. The physics code is really, really small, neat, and very clean comparing to the game code. So it's really important to make it convenient for the game programmers and for ourselves to debug it. I suggest we all can spend a couple of weeks out of a year making our life much easier. I hope that eventually Visual Studio, my Visual Studio, will look like this, just having a watch window. I tried doing this. I looked at the Visual Studio Extensibility SDK, and it was at the time kind of hard to do this way. Maybe it's easier now, I don't know. I hope everybody knows what AutoExp and NetVis files are. If not, you should look it up. And every time you find yourself clicking through the watch window, you should probably, like after 15 seconds, stop and make the data structure you're clicking through, put it into AutoExp, so that the next time you see what you want to see immediately, or at least with a couple of clicks. I told already that I'm just publishing a physics world root pointer, and the Snooper can snoop that. So I recommend that as a way to organize your data structures. Also, out-of-game visualization doesn't have to use ReadProcessMemory API, obviously. It can use TCP/IP, and many physics engines use this. Unfortunately, it eats a lot of CPU if you stream a lot of detailed data, and you would have to stream a lot of detailed data to get the effects that I just demonstrated about putting a breakpoint inside the solver and seeing the effect of each individual solve. But it works for many engines, so it's a viable option. You could use shared memory instead of ReadProcessMemory API. It has some drawbacks too. We are running out of time, so my conclusion. The most important conclusion that I really hope you come home with is you need to make work more fun. It pays to do that. If it's easier, you'll be more productive, you'll make more money, whatever you want to do, it just will be better. So with this, I probably have time for like 2 questions. Maybe 3 questions.
Hi. Great lecture, by the way. What do you do about the entire object hierarchies? You know, you serialize pointers as well, right?
Well, for the pointer, I'm just serializing how many objects it's pointing to, and I'm serializing those objects. Oh. So when I unserialize, I'm just allocating this many objects, and I'm serializing each one of them.
So you don't have, in your code, you don't have a situation where you have pointers to your children, or children have pointers to their parents?
Oh, of course. Yes, I'm sorry, of course. So this happens all the time. So the first thing, it's like a 5-liner that repeats 100 times over. It's just in my generated code. I take the pointer, that I read which pointer it is. So I'm saving the actual pointer as an ID of the object. Then I'm reading it, and I'm asking, I'm looking up in the map. Okay, have I unserialized this thing before?
Okay.
Or have I serialized this thing before?
Let me just stop you. We use the same principle, but what worries me, if we tried to use such an approach, we would get pointers to world entities, and we could take the entire world state.
That's true. That's fine with me. Like, I serialize everything.
Do you do that?
Yeah. So I cut off at some point, so like if it's pointing into the game and I don't want to serialize it, I just cut off by serializing that particular pointing manually and just serializing just the number or saying null. But in general, I'm fine with serializing everything. That's fine. If the file is 100 megabytes and I can load and I can replay all its conditions, that's actually a plus for me. Like, this is debugging technique. This is not to ship to the customer.
Yeah, but the numbers for the number of classes you serialize is pretty low, so it seems a bit isolated.
It is. It is mostly, in my case, for the physics engine, yes.
Yeah.
So it serializes the physics. It does not serialize the game, if you are asking about.
Well, how do you make the cut? You say, do you put some annotations there? Do not descend into this?
That's right, yes. If I want to, yeah, I put the annotation not to serialize that, yes.
You use this Clang annotation for that? Or?
Yes, yeah.
Okay, thanks.
Yeah. I'm not sure, can we continue or do we have to? Okay, I'll be in the wrap-up room after this if you want to ask more questions. Thank you.